Hi everyone, welcome to all of you in my lecture today. So today I'm going to talk about efficiency of a plate in a distillation column. So let's try to understand this topic. So I'll be talking about 2 to 3 kind of efficiency for the distillation column. So it will take hardly 10 to 20 minutes for a discussion. So obviously, I know if I'm talking about the efficiency, so efficiency of any particular thing physically, you can say that is output upon input, right? So here also, I mean, you want to separate particular components. So how much a more volatile component is going in the vapor phase, and uh, with respect to the maximum maximum difference in concentration. So this is how efficiency can be defined for a plate in a distillation column. So I'll be talking about 3 kind of efficiency. First one efficiency, that is your overall efficiency. So I'll be denoting it as E note. So E note can be defined as it measures the performance of distillation column. Hence, it is also called as a column efficiency. Fine. And if you want to write more elaborately, because sometimes they can ask you some assumptions based question. So the assumptions over here while calculating the column efficiency is that the plate efficiency for each plate remains constant. So while calculating the overall efficiency, it has been assumed that the plate efficiency is constant for all the plates. So the efficiency that is equals to number of theoretical stages divided by number of actual stages, right? So if I'm talking about the overall efficiency or column efficiency of a distillation column, so where number of ideal or theoretical stages you can calculate by using the Murphree diagram. If you remember that concept, so that Nm, that is your number of ideal stages, that is equals to ln x3 upon 1 minus x3 upon xw upon 1 minus xw divided by ln alpha bar. So this one is the formula for calculating number of theoretical or ideal stages while using the Murphree diagram, and from there you can calculate this particular number of theoretical and ideal stages, and after that number of actual stages will be given to you, and you can calculate this particular value from there, right? So this one is your overall efficiency of a distillation column. Now second one that I'm going to talk here is the Murphree plate efficiency. Just wait 1 second, it's not working. So here what I have told you that in case of distillation column over here, while calculating the overall efficiency of the distillation column or column efficiency, just wait 1 second. So generally it's just a simple mathematics over there that we have calculated all overall number of trays in distillation column in mass transfer when I was talking about calculation of number of theoretical stages. Now if I'm talking about the Murphree plate efficiency. I will be denoting it as EM. So, I mean, formula-based questions can be asked, and you'll have to use some, a bit kind of tricks, and definitely you'll be able to solve this kind of question. So here, what sorts of assumptions they have taken, because assumptions are very important over here. So first assumptions is that there is a uniform mixing in the liquid in axial direction as well as in vertical direction. What does it mean? Just try to understand. Let's say if there is a tray on the distillation column, right? This one is the tray, and this tray used to look like this way, right? So what happens over here? So you will see the liquid will be there on this particular tray in this form, right? If you remember the concept from my last lecture. So if I'm talking about variations of concentration in this direction and in this direction, as well as along this direction. So if I'm talking about y and x, so let's say this concentration of more volatile component is there. So I will be talking about del c by del y, that is equals to del c by del x, that will be equals to 0. Means along the axial and radial, I mean vertical and horizontal direction, that is again I am writing del c by del x, that is equals to del c by del y, that is equals to 0, where c will be in terms of mole fraction, right? So this is some sorts of assumptions that has been taken while defining the Murphree plate efficiency, right? So uniform concentration will be there, so there won't be any concentration gradient along the axial and vertical direction on a single particular tray, right? So if I'm talking about this one is distillation column having number of trays is your n minus 1 n, and this one is let's say n plus 1. So if I'm talking about this particular tray, so the vapor coming out of this tray will be having a concentration yn, and here there will be a concentration yn plus 1. So the liquid which is coming out having a concentration xn, that will be coming out over here is xn minus 1, and the liquid that will be leaving is xn minus 1. So let's say I want to calculate the efficiency of this tray, right? Our efficiency of the nth tray. So how I can calculate the efficiency of nth tray? So I will be writing Murphree efficiency EM, that is equals to actual change in composition upon maximum change in composition. So this is how the Murphree efficiency, plate efficiency can be defined. So if I'm talking about actual change in composition, it's very important to understand over here. What is actual change in composition? So the actual change in composition can be written as what? Yn minus yn plus 1, and maximum change in composition can be written as what? Yn star minus yn plus 1. Why I'm talking about yn star? Because this one is your, if I'm talking about yn star, that is your equilibrium composition. So yn star can be written as alpha xn, right, divided by 1 plus alpha minus 1 xn. If the equilibrium relation is given like that, so from here xn will be known to you, you can calculate yn star, right? So this is your equilibrium relation. So the composition of I mean, maximum change in concentration will be yn star minus yn plus 1, and where yn star is the equilibrium composition, which will be in the equilibrium with the liquid leaving to the that particular tray, which is your xn. So xn is the liquid composition that is leaving on the particular tray, and that will be in the equilibrium with the yn. So that's why yn star is the equilibrium composition. And from here yn star, you can calculate the alpha xn upon 1 plus alpha minus 1n. So if I want to write Murphree plate efficiency em, so actual change in composition, so that is equals to yn minus yn plus 1, and maximum change in composition, that is equals to yn star minus yn plus 1. So this is how you can write the Murphree plate efficiency, right? And if I'm talking about Murphree plate efficiency, so Murphree plate efficiency is referred to the gas phase. Generally, this is used for gas phase. So if you want to write the Murphree plate efficiency for the gas phase composition, so you can write the Murphree plate efficiency in this way. So I mean, here you can also write in terms of gas phase. So, but if you want to write Murphree plate efficiency in terms of liquid phase composition, so in case of liquid phase composition, Murphree plate efficiency can be written as xn minus 1, right, minus xn divided by xn minus 1 minus xn star, right? So this is how one can write the Murphree plate efficiency in terms of both your gas phase composition and liquid phase composition. Okay, thank you all. In the next lecture, I will be talking about the Murphree plate point efficiency and how Murphree point efficiency can be greater than the Murphree plate efficiency, and the efficiency can be more than 100%. Okay, thank you all for watching the video. If you have not subscribed my channel, please go and subscribe the channel, and don't forget to subscribe the bell icon. Right? Thank you all.